In the last lecture, we started with the hashing. Hashing is a technique to implement the insertion and deletion of an element, at the same time searching of an element within a constant average time. We have seen a data structure called hash table, which looks like similarly like our array data structure, in which we are going to find a suitable index to insert an element. This particular index will be calculated with the help of a hash function. There exist several hash functions. Varieties of hash functions can be used. However, the ultimate aim of hash function is to be computed, or the formula to be computed as simple as possible, and to find the index value. In this process, we have the categories such as direct addressing, modulo arithmetic, folding, and mid-square method. These are the four popular methods that are used for calculating the index value. In these four methods, the simple and easiest method, and that will be computed within is very fast, is modular arithmetic. So we have considered the modular arithmetic, in which the representation will be like this. The formula representation: h of x is equal to x mod t size, where x is the key that you are trying to insert into the hash table. So x mod t size is the table size. So you may fix a table size previously, and at the beginning of the hash table construction. So this t size is the table size. The table size will be used here for this purpose, and the key value will be moduloed with the table size. And in this, some recommendations we have made. That is, always it is better to take the table size as the prime number, and it is important to choose hash function carefully when the key is not a short string or integer. So the reason for why we need to take the table size as the prime number means to avoid a difficulty of the hash table, which is called collision. So what is this collision? If two non-identical identifiers calculate or produce same address, then it is called collision. That means if two non-identical keys, after computing the hash value, then if it is giving the same index, then it will lead to collision, because you cannot allot two keys in a single slot. So this is what the collision means. In order to resolve this collision, we have several methods. In this, two popular methods are separate chaining or open hashing. Another one is open addressing or closed hashing. These are the two methods in which we have seen the discussion of open addressing or closed hashing in the last lecture. In this method, if a collision occurs, then the uh, alternate cells are tried until an empty cell is found. This hash value is used to access the data from that address, or used to insert the data into that address. Hence, this is called open addressing, and has given different collision resolution strategies. In this open addressing, we have four categories. One is linear probing, second one is quadratic probing, third one is double hashing, and fourth one is rehashing. Linear probing is nothing but the whenever any collision occurred, and that particular index value where the collision occurred, that will be incremented by 1. That means that will be incremented by then the time that the collision was occurred, whether it is for the first time or second time or third time or like that. So the corresponding index plus that particular value, that is collision time value. So this method is used when there is a collision for a particular key. If collision is a key data, then the new hash function is like this: h of I, that is where I is the time when the collision was occurred. So when you are computing this hash value for the first time, I is equal to 0. H of x, x is the key, is equal to hash of x plus f of I mod h size, where h size is the size of the hash table, hash of x is the hash value, that is hash of x is equal to x mod 10. So whatever the x mod 10 value is there, whatever the index will be returned, that value. In linear probing method, so f of 1 I is equal to I for all I is equal to 1, 2, 3, and so on up to h size. So this particular I value to be incremented till the hash size. Now let will see an example. We want to insert the keys 49, 11, 22, 39, 61 and 72, and the table size is 10. Here the table size is 10, so x is equal to 49, the first value you are supposed to take, and you want to insert into the table. Then 49 mod 10 is equal to 9. So 49 will be placed at the ninth position straight away. That means h table of 9 is equal to 49. X of 11, x is equal to, sorry, second value is 11, x is equal to 11. Now the key 11 to be inserted. 11 mod 10. So the resultant value is 1. So check for the emptiness of the 1, index 1. So in 1, there is no element available. So directly you place the 11. That is h table of 1 is equal to 11. Next, x is equal to 22 mod 10, which is the next key to be inserted. So it is resulting into the index 2. So 22 is placed at the second position. The reason is in the second position there is no key. So directly you can place the 22 value, 22 key in the index 2. Next, x is equal to 39 mod 10 is equal to 9. Ninth position is occupied by the 49 because already 49 is the key which is already inserted because it came first and the hash value resulting into the index 9 and it was already placed in the ninth position. So here x is equal to 39 mod 10 is equal to 9. Ninth position occupied by 49. So collision occurs if it is resolved by h of x. So we need to use the formula h of x is equal to hash of x. So what is the hash of x value? You got 9. Okay, you got 9 as the hash of x value plus f of I. You got this collision for the first time. So 1 need to be added here. So 9 plus 1 is equal to 9 plus 1 mod 10. So 9 plus 1 is 10. 10 mod table size, that is 10. 10 mod 10 is equal to 0. So check for the index 0. So in the index 0 there is no key occupied. So directly this 39 will be placed in the index 0. Next, x is equal to 61 mod 10. So here 1. That means 1 is the index you are supposed to check for. Already 11 is the key available in this index 1. So first position occupied by 11. So resolve the collision using new hash function. h1 of x is equal to 11 plus 1 mod 10 is equal to 2. Again, second position occupied by 2. So use another hash function to resolve the collision. So that is what the second hash function. So because you have this particular index 1, so 11 plus 1 is also is equal to that is index is equal to 2. So here here it is not 11 actually. Here the index of the 61, that is x is equal to 61 mod 10 is equal to 1. Here it should be 1 because we are supposed to, according to the formula, this is hash of x. Whatever is the hash of x, that hash of x will be considered. So here this is 1. Okay, so it is 1. 1 mod 10 is equal to 1 mod 10. So 1 plus 1 mod 10, which is 2. Again, second position is occupied by 22. So we use another hash function to resolve this. So what is the another hash function? So this is the collision occurred for second time. So the previous index 1 plus 2, which is 3 mod 10, that is 3. So now the third position, look for third position is vacant. So directly we can insert the element 61 or key 61 into the third position. Like that, you take the second next element, that is next key, that is 72. 72 mod 10 is equal to 2. So second position is not vacant. So use another hash function. 2 plus 1 mod 10 is equal to 3. Recently we have inserted key 61 in 3. So this 3 is also occupied. So again perform the do the other hashing. That is 3 plus 1 mod 10 is equal to 4. This is the fourth position that need to be checked. So fourth position is vacant. So directly this 72 will be placed in the fourth position. So this is the way you are going to check for the alternative cells. So the ultimate aim is in this method, if a collision occurs, then the alternative cells are tried. So how these alternative cells are tried? You have used a formula, simple formula that h of I, hi of x is equal to hash of x plus f of I mod h size. So this is the way you have gone for. Then what is the drawback of this? If you keep on doing like this, how many how many times you need to check for the empty slots. So that is the reason, because that any key that hashes into the cluster will require several attempts to resolve the collision, and then it will be added to the cluster. Cluster in the sense here the hash table. What is the pool of keys that what we are having? That is the key, cluster. So that is the reason this particular problem is said to be primary clustering. Okay, so our linear clustering, we can say this is the primary clustering. The primary clustering means we need to linearly solve many computations, the hash value to be computed for many times whenever any collision occurs. This will be done in a linear fashion, because you are simply going from 1 to 2, that just by incrementing this value, that is I value, from 1 to 2, 2 to 3, 3 to 4, like that up to hash table size. So that is the reason this particular problem is said to be primary clustering. To overcome this problem, we are going for the quadratic probing. So before moving on to that, let we'll see how this particular program looks like. So this is the program for the linear probing. Drawback of the linear probing is primary clustering. So here I have defined a table size of 11, because I have taken the prime number here, prime number for table size. So I have declared a prime number for table size. So simply, and I have taken an array, declared an array of table size, that is 11. Now first initialization of the table was done. The initialization of table is int I is equal to 0, I less than t size I plus plus, h table of I is equal to -1. Like that, inserting the key. In inserting the key, first what you are supposed to compute? Key modulo t size. So the key modulo t size is assigned to hash value and some index j. Okay, so two variables is holding this value. The reason is I want to cross check whether the same index was repeated again or not. So while flag is equal to 0 and h table of j, that is the index value or the hash value that was created, is not equal to -1. That means if it is -1, initially the table is empty, so the directly we can insert into the table. If it is not -1, means there exists some key. If it is not -1, then j is equal to j plus I. What is this I value? Initially I value is equal to 1, because you have got the collision for the first time. So the index value plus the first time collision. Again modulo t size. Whatever the value you got, that is j. If j is equal to h, that is whatever the computed value you got is the previously computed value, then flag is equal to 1, I plus plus, flag is equal to 1, and whenever the flag is equal to 1, this will be terminated, and this will be terminated, this particular while loop will be terminated, and if flag is equal to 1, insertion cannot be done. But the reason is you are supposed to add this I value till the hash table size. Whenever it reaches the hash table size, what will happen? It will be again rounded to the 0 and will come back. So whenever it is rounded to the 0 and will come back and increment, whenever it is reaches whenever it reaches the previous hash value that what we computed, then there is no more slot to insert. That is what the thing called insertion cannot be done. If it is not this, then you increment the I plus plus. That is I value. That means still collision occurred. Again, try for another alternative, another cell. So like that, it keeps on going. Then whenever we don't find this -1 and we have successfully inserted the key value, then this particular it will come out of the while loop. Whenever it comes out of the while loop, if flag is not equal to 1, then h table of j is equal to the key. Printf the key percentile d insertion is successful at a particular index percentile d. So this is the value we are going to insert. In order to search or delete, same procedure we are supposed to follow. So finding the key as it is, we are going to copy and paste here. This is a very simple way. The writing of this logic is important. Remaining in are very easy for computing for developing the program. So finding, we are supposed to do the same operation again and again, and we are supposed to find it. If the flag is equal to 1, finding the key percentile d failed. Otherwise, key was found. In the same way, removing key, that is deleting of the key. So deleting of the key, the same operation need to be performed. Again, you check for the flag whether it is 1 or not. If it is 1, if it is not equal to 1, then hash table of j is equal to -1. Reinitialize the table and remove that key. And display for I is equal to 0 to t size, you are just simply displaying the hash table. So these are the functions that are available, that are supposed to be defined in defining this particular hash table with the help of linear probing. So integer main, sorry, or void main initialize the hash table, init hash table, all the slots will be assigned with -1. Then printf hash table before insertion. So let us see what are the initialization values, that is -1. Then insert 49, insert 11, insert 22, insert 39, and insert 79. Here 49 means 49 modulo 11 is 9 and 39 modulo 11 is 9. So here you will get a collision. Next 79 modulo 11 is 9. So here also you will get a collision. That means here the incrementing will be done here at 39 and 79. That we'll see after the hash table insertion, that is inserting the keys into the hash table. Just I am displaying the hash table, then removing the key 49 and removing the key 22, and then we go for hash table after key removal, then display finding the keys. So for that find 49 and 79. Since 49 is removed, so we cannot find this 49, and 79 is already available in the table, so it will show that 79 is present in so and so index. Let us see the output. So here is the output. So hash table before insertion. So currently all slots were initialized to -1. Now the key 49 insertion is successful at index 5. Next 11 is 11 insertion is successful, 22 insertion is successful, 39 is successful, and 79 is successful. Next hash table after insertion. So these are the slots where the values were inserted, and you look at 49, 79. See, 79 was inserted at second position, 49 was inserted at fifth position, 39 was inserted at sixth position. It depends upon the hash computation that what we have used. Next key 49 is removed at index 5 and key 1 is removed. Then after removal, finding keys in the thing, and finding key 49 is failed because we have removed from the key, removed from the hash table, and the key 79 was found at the index 2. So this is what the output of the linear probing. The programming is very simple. The reason is here only thing is we are supposed to keep track of this particular while loop. If you might have written this particular while loop in a correct fashion, then the insertion, searching, and removal operation will also follow the same code. So this is the code for the linear probing, and the problem with the linear probing is primary clustering. Next, we will move on to the quadratic probing. In this technique, a collision occurs. Whenever a collision occurs, while inserting the key value, we use different technique. Previously, we have used linearly. Now, we are going to use the growth in a quadratic fashion. That is, instead of I am going to use I square. This is the only difference. Remaining and all are common. Okay. Whenever the collision occurs, previously in the linear probing, we have used the incrementing of the hash value in a linear fashion by adding 1 and 2, 3, 4 as the number of collisions occurred. In case of quadratic probing, what will happen is we are going to use, instead of linear growth, we are going to use the quadratic growth. In order to use the quadratic growth, I square is used. The same thing that will say, for example, 58, 29, 32, 48, 28. X, let you consider the key 58. 58 mod 10 is equal to 8. So insert 58 in the 8th position. So next, x is equal to 29 mod 10 is equal to 9. So insert the 29 at the 9th position. Next 32, insert the 32 at the second position because the modulo is 2. Next 48 you got. Now 48 mod 10 is the index 8. Whenever it is index 8, obviously at the 8th position, some 58 was inserted. So we cannot insert it again. So 8 plus 1 square, which is 1 square is 1 only. 8 plus 1 is 9. 9 more 10. In the ninth position also, you have got the some key which is already inserted. So that is the reason you are supposed to perform the quadratic probing. That is increment this value and square. So 8 plus 2 square, which is 4. 8 plus 4 is 12. 12 more 10. Again, you got the collision here. Now what you are supposed to do? 3 square. 8 plus 3 square. That is 9 plus 8 is 17. 17 more 10 is 7. So you are supposed to insert the 48 at the 7th position. So this is the way you are supposed to perform the incrementing. So finally, if you increment all these things, these are the corresponding values you will get. 8th position not vacant, 9th position not vacant whenever you are inserting the key 28. And then finally at the 4th position, you are going to get this. So you get the free slot. So that is the reason, if you look at comparatively linear probing, this quadratic probing is uh, is taking more number of iterations to get the value, because the hash table size is small. If hash table size is very big, then obviously you will get less number of computations. So this particular drawback of quadratic probing is called secondary clustering, where in case of linear probing, the drawback is said to be primary clustering, where in case of quadratic probing, the problem is said to be secondary clustering. So because there is a quadratic path, because you are going in a quadratic path, 1 square, 2 square, 3 square, 4 square, it is the growth is in a quadratic way. The elements in the path are filled except the location of outside. Even the table has some empty space or empty locations, we are unable to insert into the elements because of the quadratic growth. So this particular problem is said to be secondary clustering. Now we'll see the code for this. Now this is the quadratic probing method, and the drawback of the quadratic probing is secondary clustering. Here same thing, t size is equal to 11 I have taken, same initialization, just like linear probing only. Once you write the linear probing, just to simply copy paste the code, and instead of I here, you make it as I star I. That's all. The entire code will work like that only. So you are supposed to make change of I star I in insertion and in finding, and the same time in the removing of the key. So after doing this same operations, same function calling, same procedure you are supposed to do in the quadratic probing. In the linear probing, linearly you will go. In the quadratic probing, you will use square, where you are going to choose the path in a quadratic fashion. Now run the code. So the same algorithm, the quadratic probing is running. Here previously the hash table is empty. Now the insertion was done here. Once the insertion was done, then the finding of the key value 49 was failed, and key was found at 2 position 2. So the same values were given as the input here to check for the collision. Okay, so this is what the quadratic probing. So I hope by this time you got the difference between the linear probing and quadratic probing. Only the formula difference. The formula is, where in linear probing you will use plus I, and here I square. This is the only difference. The main problem with the linear probing is primary clustering, because you are going in a linear fashion, and where in case of in the quadratic probing, you will be having the problem of secondary clustering, because you are going in exponentially, but you are ignoring the empty spaces in between these steps. So this is what the problem called quadratic probing. Next, we will move on to the double hashing. To avoid primary and secondary clustering, we invite a technique called double hashing, in which if a collision occurs, we choose another hash function. So same hash function, instead of same hash function, we'll use different hash function to calculate, which is called double hashing. Okay. So to avoid primary and secondary clustering, we invite a technique called double hashing, in which if a collision occurs, we choose another hashing function to solve the collision. So it is called double hashing. The first hash function will be used as h1 of x is equal to key mod hash table size. Second hash function is just to subtract 1 from the hash table. Key is key mod hash table minus 1. This is second hash function. That means if you find the collision with the first one, then you use the second one. This is what the simple alternative that we are going to choose. Now let you insert the elements 17, 48, 28, 18, 27. Then x is equal to 17 mod 10 will be inserted at the 7th position, and 48 mod 10 will be inserted at the 8th position. Now 28 mod 10 is 8. Since 8 cannot be inserted, 28 cannot be inserted in the 8th slot because already 48 was occupied. So for this, you are, for the whenever the collision occurs, then you are supposed to use the second alternative, that is 28 mod 9, where you will get the index as 1. So place this 28 in the first position. So like that, you are supposed to compute this particular hash values. Whenever the collision occurs with the first hash value, you are supposed to use the second hash value and resolve. And so again, this particular using of two hash functions is also not solving our problem of collision. The reason is whenever you take the key as 27, 27 mod 7 mod 10 is equal to 7, but it is colliding with 17. And whenever you modulo with 9, that is hash table size minus 1, then still it is coming to 0, where in the 0th position 18 is available. So with this, even though you got the collision here, you don't have another hash function to use, since you have used only two hash functions. But if you cannot devise different hash functions for every collision, so this particular method will not be sufficient. Still, it is not sufficient. So that is the reason this, even though the linear probing is having the problem, secondary that is quadratic probing is also having the problem, and to overcome these two problems, even though we have gone for double hashing, still we find the problem. That means as we cannot predict the keys that we are getting into the that what we are getting into the hash table, so we cannot predict the type of keys that we'll get. So obviously there is a possibility of collision since we don't have more than two hash functions here. This is what is called double hashing. Let me look at the code for the double hashing. Here is the code for the double hashing program to demonstrate the hash function, that is double hashing. So same thing again, t size is equal to 11, hash table of t size, initialization of the hash table. Previously we have used key plus I like that. Okay, first one is key modulo t size, as it is we have taken. Here we are going to take the second hash function t size minus 1. That's all. This is the only difference. Once you write linear probing, quadratic probing is easy. Once you write the quadratic probing, change the function of I star I to j modulo t size minus 1 in case of double hashing. So this is what the code. The same thing need to be implemented during the insertion, during the finding, and also during the removal of the key. So these three, this particular thing or this particular double hashing or two different hashings will be used in these three functions. So as it is, I have used the same thing again, 49, 11, 22, 39, and 79. Then I have gone for printing of this. So I have taken three same inputs in case of these three programs that will run the code and we'll see. So here same thing again. So this is the initialization. 49 key is inserted at 5, 11 inserted so and so. Insertion cannot be done here. The same problem was occurred. So finally, all these values were inserted after resolving the second hash function. Then finally removing was done, and finding of 49 key was failed because it was removed from the table, and the key 79 was found at the index 2. So this is what is called double hashing. So to overcome this double hashing, next one is rehashing. In double hashing, the problem is because of the table size. So why can't we go for doubling of the table size so that this problem can be avoided? This is what the basic idea of the rehashing. So in the double hashing, the problem is because of the table size. Here comes with an idea that why can't we increase the table size so that to avoid the collision. So here the solution is increase the table size, create any another table with double size and transfer the elements from the old table to the new table. For example, if the hash table has exactly half of the elements or just more, then construct a new hash table and insert all the old elements or old keys into the hash table using the hash function. So in old table, let us say there exists the hash table size is 10. H of x is equal to x mod 10. The elements are like this 40, 50, 33, 56, 66, 88. Then in case of new hash table, you are supposed to modulo with 20 and replace these elements in the new hash table that we created whenever the collision occurs. Here is the old table shared with the elements are inserted into the new table. This entire operation is called rehashing. So old size is equal to get size and initialize the table 2 into old size. So this is the thing. So whenever the collision occurs, if you keep on doubling the hash table, obviously the memory requirement will become more. And if 10 to 15 collision occurs for an element to insert, then if you keep on doubling the hash table, then our problem will not be solved because still the collision occurs. But here we are supposed to compromise with the memory. We have to allocate more memory because for every doubling of the memory, obviously for every doubling of the slots, obviously the more memory is required. So it is not a feasible solution. So that means with the linear probing also we are unable to solve the collisions. We have addressed the problem, but this problem has not completely eliminated. And with the double hashing also, with the rehashing, with the quadratic probing, with the linear probing, in all these four categories, we have not addressed the problem at a full extent. Let us see the concept of rehashing. So rehashing in this, whenever the collision occurs, we are supposed to double the hash table. So here t size is equal to 11, and I have created a pointer because we need to double the hash table for every collision. So it must be done dynamically. We cannot do statically. So that is the reason I have taken a pointer, hash table, h table, and star new table, which is for the doubling value. That is after doubling the hash table, then whatever the resultant will get, that is the new hash table. Initialization. So you are aware of how to initialize this. Hash table is equal to int star malloc of size of int into t size, that is 11. Now initialize this each and every slot in the particular table. Then insert the key. Inserting of the key will be done like this. While flag is equal to 0, hash table of j is not equal to -1. Then the collision occurs. Then t size is equal to 2 into t size, and new table is like this. And again reinitialize the new table and copy the previous table elements into the new table, and finally you make you free the previous hash table and make the previous hash table as the new hash table. And if j is equal to h, flag is equal to 1, and you cannot say that you cannot go for further insertion. And the newly created hash table is assigned as the previous hash table, and new table will be free now. Now whenever the flag is equal to 1, insertion cannot be done. If flag is not equal to 1, then hash table of j is equal to key. Then printf insertion is successful at so and so. This is at the time of insertion. But for finding and searching, this much is not required. Only thing is the j is equal to key modulo size, t size, and if you get the value directly, you print it. Otherwise, you say that key finding is failed. And same way removal of the key. Same thing, like j is equal to key modulo t size, and whatever the index value will get, that index value will be checked. If the index value is -1, then finding key was failed. Otherwise, remove the particular key by assigning -1. So I have taken the input. I have changed the input from the previous program. So here, and let will run this code, and we'll see. So this is the hash table before insertion and hash table after insertion. and finding the key 66 failed, unable to remove because already it's removed. And look at whenever the collision occurs, the whenever the collision occurs, then the element that is the 10 size hash table, that is 11 size hash table, was doubled to 22. So 0 to 21, you got the index. So this is the way how the doubling of the hash function hash table will be done in case of rehash.